Suppose we have vectors u, v, and w in Rn, and suppose that they're such that u plus 3v minus 2w is 0, is the 0 vector. Well, then I can solve for any one of them in terms of the other. For instance, u can be written as minus 3v plus 2w. Or I can even write v in terms of u and w, or w in terms of u and v. But the important thing is that at least one of them can be written in terms of the other two. And because of that, the span of u, v, and w is equal to the span of v and w. That's because u is in a sense redundant. Well, okay, I've claimed that these two spans are equal, but how do we be sure that's the case? I mean, I can do proof by assertion, but that's not very useful. So let's see, if I have somebody in here, in this guy here, so if I have somebody in here, it looks like a times u plus b times v plus c times w for some scalars a, b, and c. But if I have something like this, then I can use the fact that I know that u can be written in terms of v and w to rewrite this as a times minus 3v plus 2w plus b times v plus c times w, which is minus 3av plus 2aw plus bv plus cw, and collecting coefficients, I get minus 3a plus b times v plus 2a plus c times w. This guy and this guy, they're still scalars. And so I can write everybody that's in here as a linear combination of the vectors v and w. In other words, everybody in here is also in here. So therefore u is redundant. These two sets have to be equal. Well, actually I just showed that this side is contained in this side. But if I have somebody on the right hand side, then I can write it as 0 times u plus something times v plus something times w. And so the right hand side is also contained in the left hand side. So these two sets must be equal. So that suggests that we make the following definition. A set of vectors v1 through vk is linearly dependent let's put a little squiggle under that if there are scalars c1 through ck at least one of which is not 0, such that we have a dependency similar to this. C1 times, I called it V, V1 plus dot 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 plus CK times VK is equal to the 0 vector. So let's take a look at an example. Are minus 2, 4, minus 1, 2, and 5, 6 linearly dependent? Well, we can take a look at these for a moment, and I'd encourage you to pause the video here to figure out whether you think they are linearly dependent or not. Okay, now that you're back, let's see. Well, I can write this as minus 2, 4, minus 2 times minus 1, 2, plus 0 times 5/6 equals 0, the 0 vector, because minus 2 plus 2 plus 0 is 0. 4 minus 4 plus 0 is 0. So therefore, the vectors minus 2, 4, minus 1, 2, and 5, 6 are indeed linearly dependent. Something that I do want to point out about this is that the first two are parallel. So these two, either of them is a linear combination of the other. However, the third, this guy here, is not a linear combination of the first two vectors. Next, I want you to take a moment and try and think of two vectors which are linearly dependent and two vectors which are not. Okay, now that you're back, let me give you an example, probably my favorite example, of two vectors which are not linearly dependent. The vectors e1 equals 1, 0 and e2 equals 0, 1. Now later on in this lesson, we're going to learn how to formally prove that these two guys are not linearly dependent. But I want you to take a look at these and convince yourself that there's no way that you can take something times this first vector plus something times the second vector to get 0, other than the stupid way of having both of those somethings be 0 themselves. Now, I've given the definition here of linearly dependent. However, just because that's the definition we use, that doesn't mean it's necessarily the best way to think about it. And so, to give you the best way, in my opinion, to think about linear dependence, I'm going to give you a theorem! Yay! So, here, this is the way that you should really be thinking about linearly dependent. And that's that if we have a set of vectors, v1 through vk, that are linearly dependent, that's the same as saying that at least one of them can be written in terms of the others. At least one of them can be written as a linear combination of the others. Now, the book is going to go and prove this. And I encourage you to go and look through that proof because it'll give you a better understanding of what's going on. However, I'm not going to do so, and instead I'm going to go to an example. Are e1, e2, and 0 linearly dependent? Well, we can, for instance, use theorem 2.5 and the fact that 0 is equal to 0 times e1 plus 0 times e2. But that means that 0 is a linear combination of e1 and e2. So therefore, since at least one of these three vectors is a linear combination of the others, this entire set of three vectors is linearly dependent. However, I want to emphasize that just because one can be written as a linear combination of the others does not mean that they all can. I cannot write e1 here as a linear combination of e2 and 0. I cannot write e2 as a linear combination of e1 and 0. So, motivated by this idea, I want to give you one fact. And you might be able to guess this fact based on what we just did in this example. Namely that any set of vectors containing the 0 vector is linearly dependent. And that's because I can write the 0 vector as 0 times the first vector plus 0 times the second vector plus dot 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 plus 0 times the last vector.